Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 44. In this video, we prove a theorem. Let us see the statement of the theorem. Let y be a fixed vector in a Hilbert space capital H and let fy be a scalar valued function defined on H, defined by the formula fy of x is equals to inner product of x comma y. Inner product of x comma y. So inner product of x comma y for all x belongs to capital H. Then fy is a functional in H star, that is fy is a continuous linear functional on capital H. Further, norm y is equals to norm fy. Before going to prove the theorem, we learn about this symbol H star. Right. This H star is known as conjugate space. Let us study something about this H star. Let capital H be a Hilbert space and a continuous linear transformation. F maps capital H into capital C, where C is the set of complex numbers, is a continuous linear functional or simply a functional on capital H. I repeat, capital H be a Hilbert space, a continuous linear transformation F that is defined from Hilbert space to set of complex numbers C is called a continuous linear functional. Linear functional or simply functional on capital H. So right now the set script b of H comma C. The set script b of H comma C of all continuous linear functionals on capital H is denoted by capital H star and is called the conjugate space of capital H. So remember that H star means conjugate space of H. This is nothing but script b of H comma C. This is nothing but set of all continuous linear functionals from Hilbert space H to set of complex numbers C. So remember that. And the norm of this functional is defined like this. Norm f is equals to supremum of mod f of x such that norm x less than or equals to 1. Supremum of mod f of x such that norm x less than or equals to 1. Consequently, you remember that the conjugate space of H star is also a Hilbert space. This H star is also a Hilbert space. It satisfies the Hilbert space properties. And the space H star power H star, which is nothing but H double star, this is called second conjugate space of capital H. So this is the theory behind the symbol H star. H star means conjugate space of H. This is nothing but script b of H comma C. This is nothing but the set of all continuous linear functionals defined from Hilbert space to complex numbers. And the norm of these functionals is defined by norm f is equals to supremum of mod f of x, where norm x less than or equals to 1. And this H star is also a Hilbert space. Further, H star power star is nothing but H double star. It is known as second conjugate space. Second conjugate space. And remember that there must be a natural correspondence between H and H star. So this is also important point. There must be a natural correspondence between H and H star, and this natural correspondence is an isometric isomorphism of H into H double star. Whenever it will be useful, I can repeat the same point. And also you remember one basic point. Here the norm is defined in this way, supremum of mod f of x such that norm x less than or equals to 1. The same norm, for our convenience, we repeat here, the same norm is also defined in the following ways. Norm f is equals to supremum of mod f of x such that norm x less than or equals to 1. And the second one, norm f is equals to supremum of mod f of x such that norm x is clearly equivalent to 1. And third one, norm f is equals to supremum of mod f of x divided by norm x such that norm x not equals to 0. These all three norms are equivalent to one another. All these three norms are equivalent to one another. Yes, right? Now we learn the conjugate space and we learn the norm of the functional. Now we are ready to prove the theorem whose statement is like this. Let y be a fixed vector in the Hilbert space H and fy be a scalar valued function on H defined by the formula fy of x is equals to inner product of x comma y for all x belongs to H. Then fy is a functional in H star. And further you have to show that norm y is equals to norm fy. That's it. So let us prove step by step. Let y be a fixed vector in a Hilbert space capital H. So by statement we have capital H be a Hilbert space, and fy be a not fy. Before going to write fy, we said something about y. Here let y be a fixed vector. Let y be a fixed vector in capital H. Now we define fy. Fy be a scalar valued function. Fy be a scalar valued function on capital H defined by the formula fy of x is equals to inner product of x comma y for all x belongs to capital H. Now we have to show that this fy, we have to prove that this fy is a functional on H star. Functional means it is a continuous linear transformation defined on capital H into C. So right. Further we show that norm y is equals to this point. Norm y is equals to norm fy. So here the by definition of fy of x is equals to inner product of x comma y. This inner product of x comma y is a scalar. Especially it is a complex number. We treat it as a complex number for all x belongs to capital H. That is, this fy is a mapping. From capital H to C. So right. To show that this fy is a functional on H star, it is equivalent to show that it is linear and also continuous. So we have to prove that it is a functional. So functional means you have to show that it is continuous as well as linear. So the first one, to prove that fy is linear. To prove that fy is linear. To prove that fy is linear, let us take two vectors x1 comma x2 belongs to capital H and alpha comma beta be any two scalars. Be any two scalars. Now we have fy of alpha x1 plus beta x2 is equals to, by definition it can be defined like this: alpha x1 plus beta x2 comma y, because already we said that fy of x is equals to inner product of x comma y. This is the standard definition. So fy of alpha x1 plus beta x2 is equals to inner product of alpha x1 plus beta x2 comma y. Everybody knows the inner product: alpha x1 comma y plus beta x2 comma y. So this can be written as alpha into inner product of x1 comma y plus beta into inner product of x2 comma y. This inner product x1 comma y can be written as alpha into f1 of alpha into fy of x1 fy of x1 plus beta into fy of x2. So we prove this condition. Therefore we write like this: fy of alpha x1 plus beta x2 is equals to alpha into fy of x1 plus beta into fy of x2. This condition shows us this fy is linear. This condition shows us fy is linear. So we prove that the functional fy is a linear functional. Next we have to show that it is continuous. It is continuous. So the second point condition, to prove that fy is continuous. Fy is continuous. To prove that fy is continuous, we choose for every x belongs to capital H, by definition we have fy of x is equals to inner product of x comma y. So now take mod on both sides. Mod fy of x is equals to mod inner product of x comma y. Now applying the Schwarz inequality, by applying Schwarz inequality, it can be written as norm x into norm y. So which is less than or equals to. Therefore mod fy of x is less than or equals to norm x into norm y. Let us take norm y is equals to some constant k. Norm y is equals to some constant k, where this k is greater than or equals to 0. Then obviously mod fy of x is less than or equals to k into norm x. K into norm x. So mod fy of x is less than or equals to k into norm x for all x belongs to capital H. For all x belongs to capital H. This condition shows us this fy is bounded. This fy is bounded. Fy is bounded means every bounded functional is continuous. So fy is continuous functional. So we conclude that fy is linear and as well as continuous. This shows us clearly fy is a functional on capital H. That is, this fy belongs to H star. Fy belongs to conjugate space H star. Further we have to prove that. Next we have to prove that the second part of the theorem. Next we have to prove that norm y is equals to norm fy. It is remaining to prove that norm y is equals to norm fy. So right, to prove this already we have for all x belongs to capital H, norm it is mod fy of x, or simply mod fy. Mod fy is less than or equals to norm x into norm y. Already we proved that in case of continuous function. Let it be equation number 1. By definition of norm, by definition of norm, what is norm? Norm Fy is equals to supremum of mod f of x such that norm x less than or equals to 1. Norm x less than or equals to 1. So, if norm x less than or equals to 1, then norm x into norm y is less than or equals to norm y. Now from equation 1, mod fy of x is less than or equals to norm y. Is less than or equals to norm y. So further we can conclude this. Here mod fy of x is less than or equals to norm y. So now taking the definition supremum on both sides, supremum of mod fy of x is less than or equals to norm y. So we conclude that norm fy is less than or equals to norm y. Let it be equation number 2. Suppose if y is equals to 0, and what happens? If y is equals to 0, then norm y also equivalent to 0. Norm y is equals to 0 means fy of x also inner product of x comma y gives us x inner product of x comma 0 is equals to 0. It means fy of x is equals to 0. It means fy is equals to 0. I mean 0 functional. It means norm fy also equivalent to 0. So if y is equals to 0, obviously norm fy is also equivalent to 0. Therefore, this y must not equals to 0. This y must not equals to 0. This y not equals to 0 means H is not a 0 space. H is not a 0 space. So right, continue. Now by definition, norm fy is equals to supremum of mod fy of x such that norm x is equals to 1. Let it be equation number 3. And since this y not equals to 0 means y by norm y is a unit vector. It is very trivial. If y is not equals to 0, then y by norm y is a unit vector. Now calculate norm of y by norm y is equals to norm y by norm y, which is equals to 1. So define x is equals to y by norm y. Then from equation 3, this one. Then from equation 3, norm fy is greater than or equals to mod fy of y by norm y, which is equals to inner product of y by norm y comma y. Again this can be written as 1 by norm y into inner product of y comma y. 1 by norm y into inner product of y comma y means norm y square. So obviously you get this y and this norm y get cancelled, you get norm y. What you have now? Norm fy is greater than or equals to norm y. Now rewrite this equation, norm y less than or equals to norm fy. Let it be equation number 4. Now combining equation 2 and either this is also equation number 4, either this one or this one. Now combining equation 4 and see equation number 2, norm fy less than or equals to norm y. Here what you get? Norm fy greater than or equals to norm y. So combining equations 2 and 4, what we get? We get norm y is equals to norm fy. What is required? This completes the proof. Of the theorem, hence proved. So observe that. So one of the lengthiest theorem. In this video we learn conjugate space, and we learn about conjugate space, second conjugate space, and also a theorem which is whose statement is like this, and y be a fixed element, fixed vector in the Hilbert space H, and fy be the scalar valued function over capital H defined by fy of x is equals to inner product of x comma y. Then this fy is a functional, and also norm y is equals to norm fy. So one of the, if you know the basics, then the proof of this theorem is very simple and easy. Keep learning. Wish you all the best. In the next video, we will learn one very important theorem which is known as raised representation theorem for continuous linear functionals on a Hilbert space. Keep learning. Wish you all the best.